guys, Mr. Backerberg here. Lesson 2.7 is all about solving nonlinear inequalities. Here in part 1 we are going to solve some polynomial inequalities, and we're also going to solve a rational inequality. So here's the process that we're going to go through when we're solving a nonlinear inequality. Step number 1 says we're going to find all the zeros of our function. Those zeros are going to become our critical numbers, and we're going to use those critical numbers to set up some different test intervals. Then what we're going to do is pick a representative value from each test interval to plug it in and decide if the interval is going to be a positive interval or a negative interval. And then what we're going to do is pick out the intervals that match what we're looking for and graph out our solution. So here's the first example we're going to take a look at. We're going to solve this inequality that says x squared minus 2x minus 3 is less than 0. So like I said, the first thing we're going to do is find all of the zeros of this function. So instead of having this less than 0 thing, I'm just going to pretend that it says equals 0. So x squared minus 2x minus 3 equals 0, and we're going to go through and solve this thing. Since it's quadratic, we can try to factor it out, and I do think this one factors out nicely. I think we can go x minus 3 and x plus 1 equals 0. Set each one of those equal to 0 and solve. So x minus 3 equals 0 means that x equals 3. And this one over here, x plus 1 equals 0, means that x equals negative 1. Now what we're going to do is use these zeros to set up our test intervals. So when we're writing out these intervals, we need to think about those x values. And we always start at the very smallest x value, which is going to be negative infinity. Now we're going to go until we hit our first 0, which is at negative 1. Now since this is just a less than inequality, it doesn't have the equals to sign underneath that. When we're writing out these intervals, it's going to get parentheses since these end values are not included. Since we ended our first interval at negative 1, that's where I'm going to open my next interval, and then again go until we hit another one of these zeros or critical numbers. So we're going to go until we hit 3. Since we closed at 3, we need to open another interval at 3. Now there's no other zeros that we're going to run into, so this last interval is going to run all the way out to infinity. And now what we want to do is pick a representative x value from each one of these to plug it into our function and evaluate it. So I'm going to look at this first interval from negative infinity to negative 1. We want to pick a test value between negative infinity and negative 1. So maybe we decide to plug negative 2 in for our x value. If we do plug in negative 2 to this function for x, we're going to get back an answer of 5. Since our answer is positive, what that means is that this first interval is what we call a positive interval. If we look at our second interval from negative 1 to 3, a nice test value in there would be 0. So we plug in 0 for our x's, we get negative 3 as our answer. So that tells me this middle interval is a negative interval. And then we're looking at our last interval from 3 to infinity. I'm thinking maybe we could plug in 4. So we plug 4 in for our x's. The answer we get back is 5, which tells me that this interval from 3 to infinity is a positive interval. Now, if we go back up to the top, we were looking for where this function was less than 0. So thinking about what's going on with those intervals, less than 0 would mean negative. So I'm going to focus on this negative interval right in here from negative 1 to 3. That's going to be our answer. So we're going to go down to this number line, and we're going to graph out that interval from negative 1 to 3. Since we wrote out our interval using parentheses, that's also how I'm going to graph this out. Negative 1 has a parentheses around it, so on our number line, I'm going to put parentheses around negative 1. 3 also has parentheses around it, since those end values are not included. And all of the solutions to this inequality would be the stuff that's between here. So I'm going to shade between these two parentheses that I just drew in. Okay, so that's the answer for this interval. It's those numbers between negative 1 and 3. We can use our calculators to check our answer. I've already got the equation typed in here, x squared minus 2x minus 3. When we graph it out, we get this parabola shape. We were looking for where this was less than 0, and we said it was going to be between -1 and 3. Well, graphically speaking, those y values on our graph between -1 and 3 are negative, so those things are going to be less than 0. So that's why that's our solution. Running through this example, we're looking at x squared minus x minus 6 is less than 0. Just like I did on the last example, I'm going to start by setting this expression equal to 0 so that we can go through and find the zeros. I think we can factor this one again. X minus 3 and x plus 2 equals 0. Solving each one of those, x minus 3 equals 0 means that x equals 3. X plus 2 equals 0 means that x equals -2. Now, looking at those test intervals, remember we always start at -infinity, and we're going to go until we hit our first 0, so that happens at -2. Since we closed that interval at -2, I'm going to open the next interval at -2, and we're going to go until we hit our next 0, which is at 3. Since we ended that interval at 3, we have to open our next one at 3. There aren't any more zeros, so this last interval is going to go until we hit infinity. Now, I did use parentheses everywhere on here because it's just less than. There's not that equals to bar, so we don't have to use any square brackets. Now that we have our test interval set up, we need to pick out a representative value to plug in and decide if our interval is positive or negative. So in this first interval between -infinity and -2, maybe we decide to plug in -3. Well, when we plug -3 in for our x values, we're going to get back an answer of 6. Well, since that 6 is positive, that tells me that this first interval is a positive interval. Now, if we look at that next interval from -2 to 3, I'm thinking 0 would be really easy to plug in. If we plug in 0 for our x's, we get back -6 as an answer, so that tells me that this middle interval is negative. Looking at our last interval from 3 to infinity, maybe we pick a test value of 4, plug that in for our x, and we get back a y value of 6, which means that this last interval is also positive. Now remember, we were looking for where this x squared minus x minus 6 was less than 0. Well, numerically speaking, things that are negative are less than 0, so I'm focusing on this middle interval that runs from -2 to 3, so we're going to graph that one out. So let's say 0 is right here in the middle. That means -2 is down here on the end. 3 is on the right-hand side. Our interval has parentheses on both sides, so when we graph it out, we have to put parentheses on both sides, and we are going to shade between the -2 and the 3. So there's our solution. It's all the numbers between -2 and 3. If we were to graph this one out on our calculator, we can see that our graph is below the x-axis, between those x values of -2 and 3, which means that our graph is negative or below 0 between -2 and 3. Now on this one, if we take a look at the right-hand side of that inequality, it doesn't say greater than or equal to 0, it says greater than or equal to -48. While when we're running through these, we want to have a 0 on one side of the inequality. So I'm going to rewrite this one by adding the 48 over. So now it's going to say 2x cubed minus 3x squared minus 32x plus 48 is greater than or equal to 0. Now we need to go through and find the zeros for this function. Since it's a cubic, we're going to have to treat it a little bit differently though. I do think we can do a little factoring by grouping. So I'm going to group these first two terms together, and then I'm going to group the last two terms together. In this first set of parentheses, we can pull out an x squared, so we get 2x minus 3. In this second set of parentheses, we can pull out a -16, so we get 2x minus 3. And I'm going to throw an equals 0 on the end since we're finding the zeros of this thing. Now if we take a look at what's going on, we've got a 2x minus 3 in a couple of places in this equation, so we could factor that out as well. So pull the 2x minus 3 out in front, and then just write the leftover stuff in a new set of parentheses. So we've got the x squared left over from the first set, and we've got the minus 16 left over from the second set. We can do a little bit more factoring because this x squared minus 16 is a difference of perfect squares. So we can break that up a little bit. We've got 2x minus 3 We can break that x squared minus 16 up into x plus 4 and x minus 4. And then if we solve each one of these, 2x minus 3 equals 0. Add the 3 over, divide by 2. We get x equals 3 halves. For the x plus 4, all we have to do is subtract the 4 over, so we get x equals negative 4. And for this last one, x minus 4, add the 4 over, we get x equals 4. So now we're going to set up all of those test intervals. Just like we did before, we're going to start at negative infinity, and we're going to go until we hit our first 0. And that first 0 is at negative 4. Now this inequality says greater than or equals to, which means that these n values are included in the solution. So I'm going to throw a square bracket around the 4. Remember, infinities always get parentheses around them, so I'm going to leave that one the same. Since we close that interval at negative 4, we need to open our next one at negative 4, again using the square brackets around there, since the n value is included, and then go until we hit another 0. Looks like our next one is at 3 halves, and again, square bracket around there. That interval closed at 3 halves, so we're going to open our next one up at 3 halves with a square bracket. And then we have to go until we hit 4, close that one, open another one at 4 until we hit infinity, and infinity always gets a parentheses around it. Now we need to pick out some test values to plug in to decide if our interval is positive or negative. So in this first interval between negative infinity and negative 4, I'm thinking maybe we plug in negative 5. Now when I plug in the negative 5, I'm going to plug it into this red rewritten expression right here for all of those x's. So when we do plug in negative 5, the answer we get back is negative 117, which would tell me that this first answer is a negative interval since the answer we got was negative. If we look between our next set of numbers, I'm thinking 0 would be a nice choice between negative 4 and 3 halves. Plug 0 in, we get 48 as our answer, which tells me that this interval is a positive interval. If we look between 3 halves and 4, I'm thinking we could plug in 2. Well, when we plug in 2, we get an answer back of negative 12, so that tells me that this interval is a negative interval. And then if we look between 4 and infinity, maybe we decide to plug in 5. Well, plugging in 5, we're going to get back 63 as an answer, which tells me that this is a positive interval. Now we need to look at graphing this thing out. Well, after we rewrote this inequality, we said that we wanted our expression to be greater than or equal to 0. So we're going to focus on those positive intervals this time, since those are the things that are going to be bigger than 0. We've actually got 2 intervals that we need to graph out. We need to graph out an interval between negative 4 and 3 halves. So I'm just going to throw 0 in the middle here, which means negative 4 would be over here on the left, and positive 4 would be over here on the right-hand side. Graphing out that first interval between negative 4 and 3 halves. Square bracket on the negative 4, since that's what our interval has on it. Now 3 halves is at like 1.5, so I'm going to go halfway between 1 and 2, put another set of square brackets, and shade between there. Our next interval runs from 4 out to infinity. So I've got square brackets on the 4, since that's what our interval has, and we're going to shade out here towards the right, and I'm going to put an arrow on the end to show that the shading continues all the way out to infinity. There are a couple of unusual cases that we could run into along the way. This is one of them. We've got x squared plus 2x plus 4 is greater than 0. Now, as we're solving this one, I can see that this isn't going to factor out. So what I'm going to do is I'm going to run through and set up my quadratic formula real quick and see what happens when we do that. When I ran through and did the quadratic formula, I got a negative number underneath the radical, which tells me that this quadratic doesn't have any zeros to it. So really, instead of having a bunch of small intervals, we just have one big interval that runs from negative infinity all the way out to positive infinity. So when we're testing this, we can plug in any test value that we want. If we plug in 0, we're going to get 4, which tells me that this entire interval is positive. So if we're looking for the things that are greater than or equal to 0, everything is greater than or equal to 0. The reason that's happening is because if we were to graph this one out, everything on our graph is above that x-axis. So our graph is positive everywhere. Running through the next unusual case, we've got x squared plus 2x plus 1 is less than or equal to 0. We can factor this into x plus 1 and x plus 1. If we go through and solve each one of those, x plus 1 equals 0 means that x equals negative 1. And we've got another x plus 1 equals 0, so we get x equals negative 1 again. Setting up those test intervals, we go from negative infinity until we hit the first 0, which is at negative 1, parentheses around infinity, square bracket around negative 1. Now, since we closed that interval at negative 1, we need to open another interval at negative 1 and go until we hit our next 0. Well, our next 0 is also at negative 1. So that means just that singular value of negative 1 is itself an interval. Since we closed at negative 1, we need to open back up at negative 1 and go until we hit infinity. If we look at testing out these intervals between negative infinity and negative 1, maybe we decide to plug in negative 2. Well, when we do that, we get back 1 as an answer. So that tells me that this first interval is positive. Now, negative 1 is the only number in that second interval. So that's the only thing that we can plug in there. Well, when we plug in negative 1, we get 0. Now, since we got 0 as an answer, this interval really isn't positive or negative. It's just at 0. If we look at the interval from negative 1 to infinity, let's say we plug in 0 there. Well, plugging in 0, we get 1 as an answer. So this is a positive interval. Since we were looking for where this was less than or equal to 0, well, the only thing we've got as an answer then is this negative 1 interval, since that's the only place we ended up with 0 as an answer. So we just get negative 1 as our singular answer. Taking a look at our last unusual case, we've got x squared minus 4x plus 4. This factors into x minus 2 and x minus 2. So when we solve each one of these, x minus 2 equals 0 means that x equals 2. And the other x minus 2 equals 0 means that x also equals 2. So this is going to be a lot like that last example where we end up with an interval that just contains a singular value of 2. So there are my 3 test intervals from negative infinity to 2, 2 itself, and then 2 out to positive infinity. Evaluating each one of these intervals, if we look between negative infinity and 2, we can just plug in 0. Well, if we plug in 0, we get 4, so that tells me this first interval is positive. If we plug 2 in, since that's the only thing in that middle interval, we're going to get 0 as an answer. If we look between 2 and infinity, well, we could plug in 3 there. When we plug in 3, we get 1 as an answer, so that tells me that this end interval is positive. Since we're looking for those intervals that are greater than 0, we want the positive intervals. So that goes from negative infinity to 2, and then from 2 to infinity. But what we have to remember is that this end value of 2 is not included. So we have a special way of writing that. We take this first interval, put kind of a U-shaped thing between it with our second interval. So what that means is it's the union, okay, this U means union, of these two intervals, which means like this first interval and this other interval, but we have to remember that 2 itself is not included. So we've got parentheses on this first interval pointing left, parentheses on the right interval pointing right towards infinity, but 2 is the only thing that is not a solution in this case. We just got done dealing with rational functions, so we're going to take a quick look at rational inequalities. In order to find the critical numbers for a rational inequality, we want to set the numerator and the denominator both equal to 0, find our zeros that way, and then we can set up our test intervals and see what happens with those. Now before we get started on this example, remember we have to have a 0 on one side of the inequality, so I'm going to subtract the 3 over. So we end up with 2x minus 7 over x minus 5 minus 3 is less than or equal to 0. Now we need to put these fractions together, and in order to do that, we're going to need a common denominator. So I'm going to take this 3 over 1 fraction and multiply both top and bottom by x minus 5. So we get 2x minus 7 over x minus 5 minus 3 times x minus 5 all over x minus 5 is less than or equal to 0. I'm going to distribute this 3 through there so that we can put our two fractions together. We get 2x minus 7 minus 3x minus 15 all over x minus 5 is less than or equal to 0. I guess I'm going to need a little bit more room here. Now I'm going to distribute this negative and combine some like terms. So 2x plus a negative 3x is negative x, and negative 7 plus 15 ends up being plus 8 all over x minus 5 is less than or equal to 0. Now we can find those critical numbers by setting the numerator and denominator equal to 0. So we take negative x plus 8 and set that equal to 0. We get x equals 8. If we take x minus 5 and set that equal to 0, we get x equals 5. Those are our critical numbers, so we're going to set up those test intervals. First interval always starts at negative infinity, goes until we hit our first 0 at 5. Now I know it says less than or equal to 0, but 5 cannot be included because we'd get 0 on the bottom of the fraction. Then we go from 5 to 8. 8 can be included since we don't end up with any domain issues, and then we run from 8 out to infinity. If we test out these intervals, the first one is negative, middle one is positive, and the right one is negative. So the answer, the things that are less than or equal to 0, would be these two outside ones. So let's say 5 is right here. We've got an interval running from 5 down towards negative infinity. Then we've got another interval going from 8 out to positive infinity. So those two portions of our picture are the solutions. That's it as far as this video goes. Please remember to fill out the Google form linked in the description down below, and thanks for watching.